Okay, so uh, stepping into chemistry, it can feel a bit like, learning a whole new language,
Right,
right?
absolutely. Suddenly you're dealing with things you can't see, these tiny particles. It's a whole different world.
Yeah, concepts that aren't exactly intuitive at first
It's
glance.
like needing to learn the alphabet before you can read.
Exactly. And that's really what we want to do in this deep dive. Get you really grounded in the absolute fundamentals, the atom, the tiny building block of everything.
Mm-hmm. And we're working directly from the notes and materials you've got for your course, looking at atomic structure, nuclear symbols, isotopes, the real core stuff.
Right. Our mission here is basically to unpack those sources together, pull out the key ideas, and help you build a super solid foundation for that fundamentals of chemistry course.
Couldn't have said it better. Let's dive in.
Okay, so first things first, what is an atom? The basic definition you've got.
Right, from the source material. It's the smallest particle of an element you can break it down to. While it still is that element, it retains the properties.
Mm-hmm. So you can't chop a gold atom in half and still have gold, essentially.
Exactly, that's the limit. And, your notes hint at this, but the idea wasn't always obvious. It took centuries of thinking and experimenting to arrive at our current picture of the atom.
A long search. It wasn't just, poof, here's the atom.
Definitely not. And part of that discovery was realizing atoms themselves have parts. They aren't just tiny, solid balls.
Ah, the subatomic particles.
Yes. The big three found in pretty much every element: protons, neutrons, and electrons. Your notes list their properties, which are really important.
Okay, let's walk through those. The electron first, symbol A.
Yep, the electron. Relative charge is -1. Tiny negative charge. The absolute value is there too, -1.6022 times 10 to the -19 coulombs. But the -1 is easier to remember.
And its mass. Wow, it's listed as 0.000548 AMU. That sounds incredibly small.
It is almost negligible compared to the others. In grams, that's 9.1009 times 10 to the -28 grams. Vanishingly light.
Okay, then the proton, symbol P.
Proton, p relative charge +1, so equal and opposite to the electron's charge, same absolute charge magnitude, just positive.
And its mass, 1.0073 AMU. Okay, so way heavier than the electron.
Much, much heavier, roughly 1,800 times heavier, actually. Its absolute mass is 1.673 times 10 to the -24 grams.
Right. And the third one, the neutron, N.
The neutron, name gives it away. It's neutral, relative charge 0, absolute charge 0.
And its mass, 1.0087 MU. So very close to the proton's mass.
Extremely close, just fractionally heavier. Absolute mass, 1.675 times 10 to the -24 grams. So basically you have two heavy particles, the proton and neutron, and one very lightweight particle, the electron.
Got it. And that unit you mentioned, AMU, atomic mass unit. The notes define that pretty specifically.
They do. It's defined as exactly 112th the mass of one particular type of carbon atom, carbon-12. That specific atom is defined as having a mass of exactly 12.0000 AMU.
So it's like setting a standard baseline for atomic masses.
Precisely. It gives us a relative scale. And you also have the conversion factor there. 1 AMU is about 1.66054 times 10 to the -24 grams. Useful if you need to switch between scales.
Okay, so we have these three particles. Protons, +1 charge, heavy. Neutrons, 0 charge, heavy. Electrons, -1 charge, very light. What actually determines? Like, what makes an atom be a certain element? Is it the number of protons, neutrons, or electrons?
This is maybe the single most important point. It's the number of protons. Always. Yes. The number of protons in an atom's nucleus is unique for each element. That number has a name, the atomic number, and its symbol is Z.
So the atomic number Z equals the number of protons, and that tells you the element.
Correct. If an atom has 1 proton, Z1, it's hydrogen. If it has 6 protons, Z6, it's carbon. 92 protons, Z92. Uranium, the proton count is the element's identity. Change the proton count, you change the element entirely.
Okay, that makes sense. It simplifies things. It's the Z number.
It really does. And knowing that helps make sense of that standard notation you see, the nuclear symbol .xaz.
Right, that symbol. Looks a bit like code at first. Let's break it down. X.
X is just the element symbol from the periodic table, like C for carbon, O for oxygen, H for hydrogen. Easy enough.
Okay. Then Z, the subscript. That's
Whoa.
the atomic number we just talked about.
That's it. Number of protons, written down low.
And A, the superscript up top.
A is the mass number. This is the total number of protons plus neutrons in the nucleus. the heavy particles.
Ah, okay. Protons plus neutrons. So if Z is protons and A is protons plus neutrons.
Then you can figure out the number of neutrons pretty easily, right? Just subtract Z from A neutrons equals Z.
Makes sense. Let's use the example from the notes. Carbon 12. The symbol is C with a subscript 6 and a superscript 12.
Perfect. So C tells us it's carbon. The subscript Z6 tells us it has 6 protons.
Right, because it's carbon.
Because it's carbon. And the superscript A12 is the mass number. Protons plus neutrons equals 12.
So if protons equals 6 and protons plus neutrons 12, then neutrons must be 12 minus 6, which is 6.
Exactly. That specific carbon atom, carbon-12, has 6 protons and 6 neutrons. The symbol tells you everything you need to know about its nucleus.
Okay, that's clearer now.
Yeah.
Wait, you said the number of protons defines the element. Does that mean the number of neutrons can change?
Yes. That's the next crucial concept. Isotopes.
Isotopes, okay.
Isotopes are atoms of the very same element, so they have the same number of protons, the same Z, but they have a different number of neutrons.
So same identity protons, but different mass.
Precisely. Because neutrons contribute to the mass number A. If you change the neutron count, you change A, even though Z stays the same.
The notes give some great examples. For carbon, Z is always 6. We saw C12, which is 6 protons, 6 neutrons, but there's also C13.
Right, carbon-13. Symbol would be C with subscript 6, superscript 13, still 6 protons, it's carbon, but now A13. So neutrons AZ, 13, 6 is 7 neutrons.
And C14 is mentioned too. That would be 6 protons and 14 minus 6.8 neutrons.
Correct. Carbon-12, carbon-13, carbon-14 are all isotopes of carbon. Same chemical element, just slightly different atomic weights because of those extra neutrons.
The oxygen examples too. O16, O17, O18, oxygen is Z8, so 8 protons in all of them.
Yep. O16 has 8 neutrons, 16, 8, 8. O17 has 9 neutrons, 17, 8, 9. O18 has 10 neutrons, all oxygen isotopes.
And the hydrogen ones are kind of wild. H1 protium, Z1, A1, that's 1 proton, and 1 minus 1, 0 neutrons.
That's right. The most common hydrogen isotope has no neutrons at all, just a single proton in the nucleus and usually 1 electron outside.
And then H2 deuterium, Z1, A2, 1 proton, 1 neutron, and H3 tritium, Z1, A3, 1 proton, 2 neutrons.
Exactly. Protium, deuterium, tritium isotopes of hydrogen.
Your notes also touch on stability and how common these isotopes are, their natural abundance.
Yes, that's important. Not all isotopes are equally stable. Some are radioactive, like C14 and tritium, and they don't exist in equal amounts in nature.
Like for hydrogen, it says protium H1 is 99.99% of all natural hydrogen. Deuterium H2 is just 0.01%, and tritium is only trace amounts.
Exactly. And for carbon, C12 is the vast majority, 98.93%. C13 is about 1.07%. And C14 is, again, trace. These natural abundance percentages become really important later when we talk about atomic mass on the periodic table.
Okay, got it. So protons define the element, Z. Neutrons can vary, giving isotopes different A. What about the electrons? Do they always match the protons?
Good question. In a neutral atom, yes. The number of negatively charged electrons exactly balances the number of positively charged protons. So Z protons, Z electrons, net charge, 0.
But atoms aren't always neutral, right? Your notes mention ions.
Correct. An ion is simply an atom, or sometimes a group of atoms, that has an overall electric charge because the number of electrons is not equal to the number of protons.
Those gained or lost electrons.
Exactly. If an atom loses 1 or more electrons, it has more protons plus than electrons. So it ends up with a net positive charge. That's called a cation.
Like the calcium example, K40 with a 2 plus charge.
Yeah.
Symbol K, subscript 20, superscript 40, then 2 plus 40.
Yep. Let's decode that. K means calcium. Z20 means 20 protons. A40 means 40, 20 equals 20 neutrons. The 2 plus tells you the charge.
So 20 positive protons. To get a plus 2 overall charge, it must have lost electrons. How many?
It must have 2 fewer electrons than protons. So
Yeah.
20 protons, 18 electrons plus 2 charge. That C2 plus ion has 20 protons, 20 neutrons, but only 18 electrons.
And the opposite if an atom gains electrons.
Then it has more electrons than protons plus, giving it a net negative charge. That's called an anion.
Examples like O16 with a 2 charge and Cl35 with a charge.
Let's do the oxygen one. OZ8A16 charge 2,5. It's oxygen, so 8 protons. A16 means 16 to 8 neutrons. The 2 charge means it has 2 more electrons than protons.
So 8 protons plus 2 extra electrons, 10 electrons.
8 protons, 8 neutrons, 10 electrons for O16 2. And for chlorine, ClZ17A35 charged neutrons. Chlorine means 17 protons. A35 means 35, 17 equals 18 neutrons. A single mu charge means 1 extra electron.
17 protons plus 1 electron, 18 electrons.
You got it. 17 protons, 18 neutrons, 18 electrons for Cl35.
And even hydrogen can form an ion. H1 with a plus charge, H plus O.
Yeah, Z1A1 charge plus O. So one proton. A1 means one equals 0 neutrons. The plus charge means one fewer electron than proton.
One proton. One fewer electron means 0 electron.
Exactly. The H plus ion is literally just a bare proton, no electron, no neutron in this isotope.
Wow. Okay, so ions are just atoms that have gained or lost electrons, changing their charge but not their element identity.
That's the gist of it. Protons, identity, neutrons, isotopes, electrons, ions, charge.
Now, let's circle back to mass and isotopes for a second. You mentioned C12, C13, C14, and the notes give their specific isotopic masses, not just the mass number. C12 is exactly 12 mu, but C13 is slightly more than 13, like 13.003 mu. C14 is 14.003 mu.
Yes, the mass number A is just a count of protons and neutrons, whole numbers. The actual measured mass on isotope, the isotopic mass, is usually very close to A, but not exactly the same, due to things like nuclear binding energy and the fact that protons and neutrons aren't exactly 1 mu each, except for C12 by definition.
Okay, so each isotope has its own precise mass, but when I look at a periodic table, for carbon, it doesn't say 12 or 13 or 14, it says 12.011 mu. What's that number?
That number on the periodic table is the atomic mass, sometimes called atomic weight. It's not the mass of any single atom. It's a weighted average of the masses of all the naturally occurring isotopes of that element.
Weighted average. Weighted by what?
By their natural abundance. Remember those percentages. Carbon is 98.93% of C12, mass 12 mu, and 1.07% C13, mass 13.003 mu, with negligible C14.
So you take 98.93% of 12
Right.
plus 1.07% of 13.003.
And that calculation gives you the average mass of a carbon atom as you'd find it in a natural sample, which comes out to 12.011 mu. It's closer to 12 than 13 because C12 is so much more abundant.
Okay, that makes a lot more sense. The periodic table number is the average mass reflecting the natural mix of isotopes.
Exactly. Mass number A is for one specific isotope, an integer count. Atomic mass on the periodic table is the weighted average mass of the natural element, usually not an integer. A subtle but really important distinction.
Absolutely. Okay, we've covered atoms, particles, identity, isotopes, ions, mass. But this is all at the level of single, incredibly tiny things measured in AMU. How do chemists actually, work with this stuff in the lab? You can't count individual atoms.
Right. You can't pick up one atom or even 1,000. You work with amounts you can see and weigh, usually in grams.
Yeah.
So we need a bridge between the atomic scale, single atoms, AMU, and the lab scale, grams.
And that bridge is the mole.
The mole. It's the chemist's favorite unit. It's essentially a counting number, like a dozen means 12 or a gross means 144. A mole just means a specific, very large number of things.
And that number is Avogadro's number, right? Your notes have it as 6.02214 times 10 to the 23rd power.
That's the one. 1 mole of anything contains Avogadro's number of those things. 1 mole of carbon atoms has 6.022 by 1023 carbon atoms. 1 mole of water molecules has 6.022 by 1023 water molecules. It's just a quantity.
A really, really big quantity.
Necessarily big because atoms are so small.
Right.
But here's the crucial connection, the part that makes it so useful.
Okay.
The mass of one single atom of an element expressed in AMU is numerically equal to the mass of 1 mole of those atoms expressed in grams.
Wait, say that again. Numerically equal.
Yes, look at carbon again. The atomic mass, the average mass of one carbon atom is 12.022 by 1023 of carbon atoms is 12.011 grams.
Whoa, so the number is the same, just the unit changes from AMU for one atom to grams for a mole of atom.
Exactly, that's the magic. That atomic mass number from the periodic table does double duty. It tells you the average mass of one atom in AMU, and it tells you the mass of 1 mole of those atoms in grams. This is called the molar mass.
That's incredibly useful. So I can weigh out 12.0102 grams of carbon, and I know I have exactly 1 mole, or 6.022 by 1023 carbon atoms, without ever having to count them.
Precisely. It connects the microscopic world of atoms and ANU to the macroscopic world of balances and grams. It's fundamental to almost all chemical calculations, what we call stoichiometry.
Okay, wow. That ties a lot together. So just to recap this whole journey, we started with the atom as the basic unit, made of protons, neutrons, electrons.
Protons, Z, define the element's identity. Neutrons varying gives isotopes, different mass number A. Electrons varying gives ions, charge.
We use the XAZ symbol to represent specific atoms or isotopes, and the mass on the periodic table is the atomic mass, a weighted average of natural isotopes.
Right, measured in AMU for single atoms.
And then the mole, Avogadro's number, provides the bridge, letting us use that same atomic mass number, but in grams, to measure out moles of atoms in the lab.
You've got it. Understanding these pieces, atom structure, symbols, isotopes, ions, atomic mass versus mass number, and especially the mole concept, that's absolutely crucial for your chemistry course. It's the foundation everything else rests on.
Definitely feels foundational. Okay, thinking about all this, especially the isotopes, atoms of the same element having slightly different masses and existing in those very specific natural abundance ratios, like the 98.93 per C12 and 1.07 per C13.
Yeah.
How might scientists actually use that slight difference in mass and those precise natural ratios? Could that subtle variation tell us something interesting in the real world? Maybe about, I don't know, where a sample came from or how old it is or something about its history.
That is an excellent question to ponder. How could those tiny mass differences and fixed ratios be exploited? Definitely something to think about as you build on this foundation.